in the given diagram, you should find the output and you have to verify the output in the 4 options. So what is the output in the given diagram? X1 plus or minus X2. If you see the option A, the output is X1 minus or plus X2. In option B, if you write the output, we are getting X2 plus or minus X1. In option C, we are getting X1 plus or minus X2. In option D, we are getting minus X1 plus or minus X2. That means the same output we are getting in only option C. So the answer is option C. Identify the correct number of individual loops. First, select the feedback path and observe the number of forward paths. For example, first I'll select a feedback path C. So the feedback path C having the how many forward paths you observe it. One forward path is A, another forward path is B. That means 2 forward paths. So it gives the 2 loops. The second feedback path, you have observed the F is another feedback path. So to this having a 1 forward path H, that means the F having 1 forward path, that means it gives 1 loop. Next, select the feedback path G. The G also having a 1 forward path H. So G having 1 forward path, that means it will give the 1 loop. Next, you select a feedback path EFI. So EFI is a feedback path. So the number of forward path to this is one is like this. The second one is through B. So that means it is having a 2 forward paths. That means it gives the 2 loops. The next feedback path is EGI. So EGI is the next feedback path. So to this also we are having through A 1 forward path and through B 1 forward path. That means 2 forward paths. That means it gives 2 loops. So total number of loops is 8. In this problem, we require to find the sensitivity. So first we find the change in G. The change in G, you find it, percentage of change in G, find it, you will get a 50%. So the sensitivity STG equal to percentage of change in transfer function divided by percentage of change in G, that equal to 1 by 1 plus GH. So percentage of change in transfer function equal to percentage of change in G divided by 1 plus GH, that equal to 50% divided by 1 plus 15,000 into 0.01. If we solve this, we will get 0.33%. So here first we require to find the percentage of peak overshoot. So here given percentage first peak overshoot MP, how much they given? So here 3.5 minus 3 divided by 3 into 100%. If find it, so you will get the 0.5 divided by 3 into 100%. So that equal to 0.5 by 3 into 100% equal to the formula for peak overshoot is e power minus pi zeta divided by root of 1 minus zeta square into 100%. So this cancel, and if you solve for zeta, you will get zeta equal to 0.495. Here R is not an input. So the Mason's gain formula gives the transfer function with respect to only input only. So we need to consider a dummy node with the path gain of 1. So that is U. But we need to find C by R. C by R equal to C by U divided by R by U. So take a here, if you find C by U, the forward path gain is 7. Both the loops are touching. So divided by delta, divided by, if you take U to R, the path gain is 1. This L1 is touching, but L2 is non-touching. So 1 plus 4 divided by delta. Delta, delta cancel. Then you find it, the answer is 7 by 5. Here we require to find the K maximum value for stability. So by using RH criteria, first we require to expand the exponential term. So that is K into 1 minus S tau. Neglect higher order terms divided by S into S plus 1. So here mention a unity feedback H of S equal to 1. So the characteristic equation is 1 plus G of S equal to 0. Then that equal to S square plus S plus K minus K S tau equal to 0. So that equal to S square plus S, take it common here, 1 minus K tau plus K equal to 0. Write the Routh tabular form. So here S square, S power 1, S power 0, 1, K, so 1 minus K tau, K. So for the K maximum value will get at marginal stability. So make equal to 0, then it is marginal stable. Then the K equal to 1 by tau. So this is the maximum value for the system stability.